this afternoon is by Koen van Dungen, and who is presently at CISA Trieste.
Thank you, and thanks also to the organizers for the opportunity to speak here. So yeah, I will be talking about the fermionic action, and then in particular the fermionic action from the Lorentzian context. So I will start with a brief introduction to, say, Alain Con's version of the fermionic action. And then I want to continue describing the way I approach NCG from the Lorentzian signature perspective, which is based on Krein spaces. Then a few words about how to introduce the gauge fields into this picture. And then finally I want to describe as an explicit example so you can see how the fermionic action really works compared to physics. I'd like to describe the example of electroweak interactions. All right, so to start, the fermionic action, as Alain Con defined it, it's defined for a real even spectral triple, and it only works in the case of KO dimension 2. And then it is defined by this formula. So we take a vector xi, which is required to be an even vector, and then we take the inner product of the real structure applied to xi with the Dirac operator applied to xi. And this tilde above xi means that we view xi as a Grassmann variable, so we assume that it's an anti-commuting variable. So yeah, first of all I should say this, on the one hand it's a very successful formula. If you, for instance, Alain Con and collaborators calculated it for the case of the standard model, and you really do get all the terms in the Lagrangian that you would expect in the standard model. So you get kinetic terms, mass terms, gauge interactions, everything pops out quite naturally. But there's still two discrepancies, I would say, with this approach. First one, of course, it's based on a Riemannian signature instead of Lorentzian signature, and we would like to do this in space-time instead of just space. But secondly, and which perhaps even worse, I would say, it involves the real structure. So basically, for spinors, it will be the charge conjugation operator. And if you go across the hallway, there's a library. You can look up your favorite physics textbook, look up the Lagrangian, and there will not be any charge conjugation in this Lagrangian. So this is also, I would consider, a serious problem with this approach. Quite amazingly, though, when Alain Con put this paper on the archive, these two problems were solved on the exact same day, because John Barrett also put a paper on the archive the same day.
No, it's the other way around. I put my paper on the archive and then he put his on.
Oh yeah, was it the other way around? I thought it was the same, but okay. I might be wrong.
No, because what happened is I put mine on the archive and I emailed him my paper and then he put his on the archive.
But they appeared at the same time?
Yeah.
Okay.
Well.
The outside world, they appeared at the same time. The problem as well as the solution, I would say. So the whole point is that both problems can be solved at once by just acknowledging that space-time is Lorentzian instead of Riemannian. And then you don't need this real structure to be present. All right, so problem solved. I can end my talk here, and we can have no. So what I want to do is part of the purpose of this talk is to give a flavor of how things work in Lorentzian signature, and part of the purpose is also that I'm going to make some small modifications to John Barrett's approach, and I will explain those changes along the way. All right, so Krein spaces. So we've seen in the talks this morning as well that for the Lorentzian setup, we make use of Krein spaces instead of Hilbert spaces. So very simply, a Krein space is like a Hilbert space, except that the inner product is not required to be positive definite. We do require it to be non-degenerate. So this means that if a vector is orthogonal to the entire space, then it must be the zero vector. But it does not mean that a vector which is orthogonal to itself must be the zero vector. You can have, say, zero length without being the zero vector. And like a Hilbert space, we need a completeness assumption on this space. And the problem is, of course, that an indefinite inner product does not define a norm, so you can't just ask it to be complete in this norm because it's not a norm. So instead what we do is we take a decomposition into a positive definite subspace H plus and a negative definite subspace H minus. And on each of these definite subspaces, the inner product does define a norm, and then you can require these subspaces to be complete in this norm. So that's what we do. All All right, given a decomposition, you automatically get what's called a fundamental symmetry. So it just acts as +1 on the positive definite part and -1 on the negative definite part. And using this fundamental symmetry, we can then turn the Krein space into a Hilbert space. And we do this simply by plugging the fundamental symmetry into the indefinite inner product. And then we get a positive definite inner product, which depends on the choice of fundamental symmetry, so which depends on the choice of this decomposition. Good thing to point out, though, is that the norms you get from these positive definite inner products, depending on J, all these norms are equivalent. So in particular, this means that the norm topology of these norms is the same for each of these choices of fundamental symmetry. So in particular, notions like bounded operators or convergence of sequences, etc., are well defined with respect to the topology obtained from such a positive definite inner product. So these are canonical notions which still make sense on a Krein space. And then lastly, I want to introduce Z2 grading for a Krein space. And the way I do this, I assume that if I fix the fundamental symmetry, then I say the Krein space is Z2 graded if the corresponding Hilbert space is Z2 graded in the usual sense. And I require that the fundamental symmetry is homogeneous, by which I mean it's either an even operator or it's an odd operator, but not a mixture of the two. And yeah, so saying that the Hilbert space is Z2 graded, so this means that the positive definite inner product respects the Z2 grading, but the indefinite inner product on the Krein space might not respect the Z2 grading. Yeah, they could commute, but so they either commute or anti-commute. Yeah. No, I assume that they either commute or anti-commute. Yeah. So I want the fundamental symmetry to be either even or odd. So either commute or anti-commute. Yeah. Yeah. All right. So the main motivating example for why we look at Krein spaces comes from the spinors on a Lorentzian manifold, or more generally on a pseudo-Riemannian manifold. So, all right, I start with a Lorentzian spin manifold, even dimensional usually, and I assume it's both space-oriented and time-oriented. And I suppose I have a given decomposition of the tangent bundle into a time-like subbundle, ET, and a space-like subbundle, ES. So the metric is negative definite on the time-like part and positive definite on the space-like part. And yeah, such a decomposition always exists. So this is always possible. But there's a choice, of course. There are many such decompositions. Given a decomposition, I write a time-like projection operator, which just projects a vector to the time-like part. And equivalently, I can also define a space-like reflection, R, which just acts as +1 on the space-like vectors, -1 on the time-like vectors. And given such a space-like reflection R, I can define a Riemannian metric just by putting the R into the Lorentzian metric. So this is simply, because the space-like reflection acts as -1 on the negative definite part, the signs cancel and you end up with a positive definite metric. And then M with the metric GR is a Riemannian manifold. All right, so given a decomposition, one can construct a positive definite Hermitian structure on the spinor bundle as well. And yeah, so we apply this positive definite inner product initially on the space of smooth, compactly supported sections. Then we complete in this inner product, and the space we get, we denote with the usual notation L2S. So these are the square integrable sections of the spinor bundle. But again, this inner product depends on the choice of initial decomposition. But then we can define a fundamental symmetry. So in this decomposition ET, the time-like part, it's assumed to be oriented. So there exists a unit section of this bundle, a unit time-like vector field E0. And we just look at the Clifford representation of this vector field. This is a self-adjoint unitary operator on L2 of S. And it's also quite neatly related to the space-like refraction, which is defined on this decomposition. And in fact, this turns out to be a fundamental symmetry of L2 of S. So we can define the indefinite inner product on L2 of S just by plugging the fundamental symmetry into the positive definite inner product. So the construction of this indefinite inner product goes through a choice of decomposition, but it turns out that the indefinite inner product you get in the end is independent of this choice. So you get a canonically defined indefinite inner product on the space of spinors. And this is why it's more natural to view these spinors as a Krein space instead of a Hilbert space, because the indefinite inner product is canonical, but the positive definite one is not canonical. It depends on the choice of decomposition.
Depends on choice of what?
This decomposition of the tangent bundle, which is equivalent to choosing this operator J, basically.
Is there any relation between different decompositions? Like sort of transformation?
Yeah, I mean, yeah, it's sort of like a boost you would think of in the tangent bundle, yeah.
J is
If you take a different,
up to such transformation.
yeah, I would say so, yeah. But yeah, you have to, yeah, it's a local boost which can vary, yeah, from point to point. All right, so we have a Krein space of spinors on the Lorentzian manifold. We can also look at the Dirac operator on these spinors. So it's defined in the usual way. It's basically composition of the Clifford representation with the spin connection, which is the lift of the natural Levi-Civita connection corresponding to the Lorentzian metric. And just like in the Riemannian case, if you want to prove that the Dirac operator is self-adjoint, you need a completeness assumption on the manifold. Here it works similarly. But now we assume that there exists at least one decomposition of this tangent bundle such that the corresponding Riemannian metric GR is complete. And in that case, it was proven by Helga Baum that I times the Dirac operator is essentially Krein self-adjoint.
What does that mean? Sorry. Essentially, self-adjoint is for the Krein product.
Right, so it means that the closure is Krein self-adjoint. And Krein self-adjoint, yeah, it means it's the usual, what you would expect, just self-adjoint with respect to the indefinite inner product.
Why do you need this kappa?
I mean, I think this is the basically what you naturally get if you compose the Clifford representation with the spin connection. So basically, I mean, it has to do with the isomorphism between the tangent bundle and the cotangent bundle, which has a minus. It uses the metric, so it has a minus sign for the time-like part. So that's you get a minus sign popping up for the time-like part.
If you wrote this out without using a frame, this is Clifford multiplication composed with the
Yeah,
reflection, then you
yeah,
get
that's what I would do. Yeah, yeah.
So it's the metric.
Yeah.
So if you were just to write the metric Gij, gamma Vi, nabla Vj, the same.
Well, if the metric is flat, I suppose. Yeah, but yeah. If you use in terms of this orthonormal frame, yeah, you put the metric there. Yeah, exactly. Yeah.
This is an inner product. This
Yeah.
Gamma J is the inner product of the Lorentz.
Of the orthonormal frame. Yeah.
Yes,
Yeah, that's right. All right. So then the So the canonical. All right. So the canonical data we want to consider is the usual. We take smooth compactly supported function on the manifold. We take the spinors. Put I times the Dirac operator because we would like it to be Krein self-adjoint. And then we will now also add the fundamental symmetry to our data. Of course, this is not going to be a spectral triple because we have a Krein space instead of Hilbert space. It's not a self-adjoint operator. So the question is, what will it be? All right, so this is the third talk today, and you've already seen definition of spectral triple in every talk so far today, I think. So I will be brief. I'll just mention that I only look at the even case. So I have a Z2 graded Hilbert space. And all the gaps in here, of course, I will be filling in once I improve this definition to become much nicer. One thing I would like to point out, though, is this last definition, which is normally phrased a bit differently. But it is equivalent to the usual definition. One would say that the resolvent of D is compact. So the way the argument goes is something like construct a commutative diagram, triangle. So you have an inclusion of the domain of D into the Hilbert space, say iota. You have an operator on the Hilbert space, which is the resolvent. And you can also consider another map, which is just D plus minus I. This diagram commutes. But the point here is that we don't just view the domain of D as a subset of the Hilbert space, but we view it as a Hilbert space in its own right. And this we do by equipping it with the graph norm of the operator D. So it will be something like this. And equipped with this graph norm, the domain of D is complete. It is a Hilbert space. And in this topology, the map D plus minus I is then, of course, a bounded operator. And it's also invertible, so we can go back. So we have bounded operators in each direction. And then it follows that this resolvent is compact if and only if this inclusion map is compact. And the same argument also works in the locally compact case. So typically I would say it's locally compact if it is compact once multiplied with an element of the algebra. All right, so now let's fill in the gaps. I will define Krein spectral triples. Of course, the change is that we replace the Hilbert space by Krein space now. And furthermore, I add an extra piece of data, namely the fundamental symmetry. I assume it's homogeneous, so it's either even or odd. And also, it's assumed to commute with the algebra. And in particular, this means that say the Hilbert space adjoint and the Krein space adjoint of the algebra are the same, because it commutes with the fundamental symmetry. So we don't have to worry about what does it mean to have a star algebra representation of a C-star algebra in a Krein space, which might be complicated if it would not commute. But in this case, it's no problem. And then, of course, the operator is assumed to be Krein self-adjoint instead of self-adjoint. And the reason why I rephrased the last condition, the compactness of the resolvent, is because now I don't have to change it anymore. The only change, though, is that what exactly this domain E is. It's not the entire domain of the operator D, but instead you take the intersection of the domain with j times the domain of D. And again, we don't just put just the graph norm of D on this space, or we take a sort of a combined graph norm of the operators JD and DJ. So note that the domain of DJ is just j times the domain of D, because j squared is 1. So this is a natural norm that one can put on this intersection of domains of two operators. And E is complete with respect to this norm, and I assume that this inclusion map is compact, or locally compact.
So can you rephrase this condition 4 in terms of an operator that you construct out of D and J?
I'm not sure.
Because there was this, so for instance, Trauma, he did this original definition where he said this should be a compact, should have
Yeah. I'm not sure if that's necessarily equivalent. Yeah, Stromae sort of has the...
Yeah, I guess so. Because this norm is very similar to their construction.
Yeah. Yeah, it's definitely very similar. I'm not sure if it's exactly the same, but it could be, yeah. But yeah, the nice way of phrasing it like this is that you can basically assume the resolvent to be locally compact without actually having existence of a resolvent. So typically, for instance, the Dirac operator on Minkowski spacetime, the spectrum is the entire complex plane. So the resolvent set is empty, there does not exist any resolvent. But this assumption makes perfect sense. And also, I haven't quite proven this, but I think typically, if you replace E by the domain of D, it's probably not true. The inclusion of the domain of D into the Hilbert space, I don't think it will be compact. All right, and one extra definition. We say a Krein spectral triple is of Lorentz type if the fundamental symmetry is odd. And it's only in this case that I will define the fermionic action. All right, so of course the main motivating example, the spinors on a manifold, a Lorentzian manifold that I described. Of course, it is a Krein spectral triple. This is, of course, what I want. And in the case of Lorentzian signature, it's also a Lorentz type spectral triple, so the fundamental symmetry is odd. Of course, it's not too difficult to get finite dimensional examples of Krein spectral triples. And I will only look at the case where the fundamental symmetry on the finite space is even. So I want the finite space to be not of Lorentz type. And the reason is that then if I still have a Lorentz type for the manifold and not Lorentz type of the finite space, then the product, the almost commutative Lorentzian manifold defined like this, is going to be of Lorentz type as well. All right, so I define, because both of them are even, I use the graded tensor product to keep track of the Z2 gradings of both of them. Yeah, and one thing probably to point out is that I put an extra I in front of the finite Dirac operator, df. And this is because even though df is Krein self-adjoint and the operator 1 is also Krein self-adjoint, the tensor product might not be Krein self-adjoint. And the reason is that the fundamental symmetry Jm is odd, and df is also odd. So in computing the Krein adjoint, you have to, there's an extra minus sign that pops up. And so I insert a factor I to make sure that this tensor product is again Krein self-adjoint. All right, so then let's move towards the fermionic action. So the basic form will be just the inner product of a vector with d times a vector. So I just want to point out that this, if you view this as a, say, a quadratic form on the domain of D, then this is going to be symmetric. This is just because of Krein self-adjointness of D and symmetry of the inner product. And second, it behaves well with respect to the Z2 grading. So if I take an even as well as an odd vector, then I get 0. And then we define what I call the Krein action to be just simply this inner product for one vector psi in the domain of D, but which is even. And because of the first property, this Krein action is automatically real valued, which is what we want. And it also behaves well with respect to the Z2 grading, which makes sure that this is well defined if we just restrict it to the even part of the Krein space. One other thing I'd like to point out is that this is entirely a classical action in the sense that I do not require psi to be a Grassmann variable, unlike what John Barrett and Alain Koen do and what was described by Nadir this morning as well. So for me, there's no assumption of Grassmann variables in here. It's just a section of a vector bundle, and that's all. And personally, I find this more natural because the entire setup of almost commutative manifolds is just that of a classical gauge theory, not of a quantum theory. And if you just have sections of a vector bundle, it's basically a vector space. For me, it's a bit unnatural to require vectors to commute or anti-commute because there's no product on vectors. So personally, I prefer this approach, but you can judge for yourself, of course. All right. So let's continue and do a little bit of gauge theory. In particular, I want to see how the gauge fields pop up in this framework. And for this, I basically follow the approach by Koen, Shamsuddin, and Walter. So I'm going to look at the perturbation semigroup. So it's defined like this. So if I start with just any unital star algebra. I look at sums of tensor products, finite sums to begin with. I can define a bar, which is just swapping the two elements and taking the adjoints in the algebra. And then I say that A is real if A bar is equal to A, and A is normalized if this sum is equal to 1. I just mean, yeah, say the algebraic tensor product without any completion. Yeah. And then the perturbation semigroup is defined as the real normalized elements in this tensor product. And because the product in this tensor product preserves these two properties, this is indeed a semigroup. All right. Now, suppose we have a Krein spectral triple for some algebra B. Then, as usual, we define the generalized one forms, just to be products of elements in the algebra with these commutators. And then we can define a map from the perturbation semigroup to these generalized one forms, which we call eta D. And it is defined like this. One observation here is that if you start with a real element, so if you start with something in the perturbation semigroup in particular, then what you get is Krein self-adjoint. And this is proved in the exact same way as in this paper, but now D is Krein self-adjoint instead of self-adjoint. And as I mentioned before, the elements of the algebra, the Hilbert space adjoint and the Krein adjoints are the same, so there's no problem there. All right. Now, I haven't mentioned anything about order 1 condition yet, in particular because I don't have a real structure even. But suppose it does satisfy the order 1 condition in this sense, so not with there's no real structure, but I can still look at the opposite representation of the algebra. If these commutators are 0, then the map from the perturbation semigroup to the one forms simplifies a lot. You just have 2 terms. And the example I will consider does satisfy this order 1 condition.
If you have the representation of the opposite algebra, do you need some conditions with respect to the Krein structure? Because
yeah, so I want it to be a star algebra representation.
Yeah, but you have the representation of an algebra and an opposite algebra.
Mm-hmm.
So is there any additional condition that you need to have between the Krein structure?
In the Krein structure, no,
No.
not really. No.
Okay.
I do assume the representation and the opposite representation have to commute.
Yeah.
So that I get a well-defined representation of the tensor product of A and A op.
And also that, but there is some, also that they commute with, taking the star in the algebra commutes with the...
Yeah, so I also want the representation to commute with the fundamental symmetry.
That's right.
Yeah,
Okay,
both of them.
yeah. So this
Yeah,
is
so
so there
the star adjoint in the algebra is
Yeah.
the same as the Krein adjoint in the Krein space, but
Which is
mostly because it's the same as the usual Hilbert space adjoint. And it commutes with the fundamental symmetry. Yeah. Right, so then we use this map from the perturbation semigroup to the one forms to construct fluctuations of the operator D. We simply take an arbitrary element in the perturbation semigroup, and then we add its image under this map to the operator. And yeah, so in the example we'll see that this will give us gauge fields as well as potentially Higgs fields and things like that. And yeah, this is a nice result where really the semigroup property comes into play. So if you do 2 fluctuations one after the other, then you get a fluctuation which responds to the semigroup multiplication in the semigroup. All right. Lastly, let's also quickly look at the gauge group. Yes.
AJ star opposite exactly space is an operator. What's this opposite?
Yeah. So I have a. The question is, what does it mean? What does this mean? So I mean that I have a representation of the opposite algebra, and I use that representation here.
Yeah, okay.
Yeah. So AJ star is an element.
mutually
Yeah.
commuting representations,
Yeah.
one of the algebra.
So I've dropped all the pi's from the notation, but yeah, that's. I mean, we have 2 given representations, one for A op, and then depending on whether there's a subscript op or not, you know which one to take.
Let me
And then
ask the
commute.
same question again. So the J that gives you the opposite representation.
Doesn't exist. Not yet.
Well, not necessarily. Just from the representation, you don't work with J.
No, I just So instead of having a J which gives you the opposite representation, I just start with an opposite representation.
But I think.
But we will see later how to relate it. The last few slides I will talk about real structure as well.
But the question is, if you have J, what's the
What's
property?
the connection
What
to the fundamental
exactly?
search?
Yeah.
I was curious of that. But maybe I will ask that later.
Okay. All right, so we can also embed the unitary group of the algebra into the perturbation semigroup via this map delta, which is then used to U tensor U star op. And then we can use just the multiplication in the semigroup to get an action of the unitary group on the perturbation semigroup. But we can also realize that this perturbation semigroup lies inside the tensor product of A tensor A op. So we can compose it with the representation of this algebra. And then this gives us an action of the unitary group on the Klein space. And we simply define the gauge group to be the image of this representation. And because this representation might have a non-trivial kernel, this gets quotiented out from the unitaries. Right, and then the point is, of course, that the Klein action, which I defined, is invariant under the action of the gauge group. So if I act on psi via this representation, and I act on A via the map delta. Now, it's a small subtlety that this is not actually an action of the gauge group, because even if I know rho u, it doesn't mean I know u. There's a non-trivial kernel. But what this implies for the fluctuated Dirac operator, it does give a well-defined action of the gauge group. So for the d subscript A, this gives you a well-defined action of the gauge group. And the Klein action is invariant under this action. All right. So now let's have a look how this works more concretely and how this relates to actual physical Lagrangian. I want to describe the electroweak theory. And the main reason I picked this example is because, on the one hand, it has sufficiently many interesting features. For instance, from the standard model, like you get a Higgs field, you can have Majorana masses, things like that. So there's enough going on. But at the same time, sorry?
Not with the commuting variables.
What do you mean?
The variables have to anti-commute to get to Majorana mass.
No.
But maybe he can.
I will show.
Oh, let's see.
I will show. Yeah, so you have interesting features, but at the same time, as most of you know, while the standard model is based on a 96-dimensional finite Hilbert space, here I will only start with a 4-dimensional space, so everything's a bit more manageable. All right, so let's see what it looks like. So let's take a finite Hilbert space, which is just C to the 4. Choose an explicit basis, which I write like this. So I'm thinking of having electrons as well as neutrinos, and for both I have right-handed and left-handed version. The Z2 grading, it is defined by letting the left-handed part be the even part and the right-handed particles to be odd. The algebra is defined in the usual way by taking the complex numbers and the quaternions. And then I have to specify two representations, one for the algebra and one for its opposite algebra, which are defined like these. So for the representation of the algebra, acting on the right-handed particles, I just act by the complex numbers via lambda and lambda bar. And on the left-handed particles, the quaternion number acts. And so I view Q as given by two complex numbers, alpha and beta, and then it acts via this matrix. And the opposite representation is very simple. It's just a scalar multiplication by the complex number lambda. And of course, here it's useful that the complex numbers are commutative, so I don't have to worry about the opposite anymore. All right, and because these two representations commute, I get a well-defined representation of the tensor product of A with its opposite algebra. And if you work out the formulas, what you get is that, again, the Q lambda and the Q act. And from the opposite part, you just have the lambda, which is now called lambda prime from the opposite.
Is this a faithful representation?
No, I don't think so. No. But all right. The,
The opposite one, or
No, the opposite one is certainly
neither one. This one isn't, and this one isn't, I guess. Well, that's all right.
Wait, pi lambda q is okay, right?
pi is okay.
Pi is okay.
Pi is okay.
Yeah.
Pi opposite.
This one is okay. Yeah.
Pi certainly.
Well, it will be in the end, but right now there's no j yet. You will see. So this is, I mean, to maybe say a little bit already. So this is, you can see this as the usual pi, but on the antiparticles which are not yet part of my Hilbert space or Krein space. It is a Hilbert space in this case. So normally you would also have two pi's, one on the particles and one on the antiparticles. I replace it with, I don't have antiparticles, but I still have two representations, one from the left, one from the right. So there's the same information in there. Yeah. All right, so I define a mass matrix on this space. So it's just two mass parameters, one for the neutrino and one for the electron. And putting everything together, I obtain a finite space. And the fundamental symmetry, I just take to be the identity operator. So in this case, we just have an ordinary spectral triple.
So
There's no Krein space structure. Sorry?
You don't put Majorana masses?
No, not yet. I will in the last few slides, but at the moment there are no Majorana masses.
We need another copy of the...
Then we will need the antiparticles. Yeah.
Could be an
No, I mean in this four-dimensional space, there's basically no space to introduce the Majorana mass. No. But everything else is there. So this is why I present it like this. Where we get everything except for the Majorana mass. Right, so you can calculate the gauge group, just to mention quickly. So the kernel of this representation will just be plus minus 1. And these are just the unitaries of the complex numbers and the quaternions. So we get the correct gauge group that one would expect for electroweak interactions, up to maybe a finite part.
I don't understand, because the Dirac mass connects the antiparticle to the particle.
No.
Not in this case.
No, normally it connects left and right, not particle and antiparticle.
Okay, yes.
And that's the same thing here, yeah. All right, so we will consider the almost commutative manifold, the same as what I showed before. So what we have here is basically we have the fermionic particles, our matter fields. We have mass terms, we can generate kinetic terms, but there is no gauge interactions just yet. So this is why I talked about the fluctuations of D. So if you take an arbitrary element in our perturbation semigroup for this almost commutative manifold and consider the fluctuation of D, then what you will end up with is something of this form. So what is being added is this field A mu. So the way it acts is like this. So there's no gauge action on the right-handed neutrino. This one does not have any interactions. We have a U1 interaction on the right-handed electron. And on the left-handed particles, we have both the U1 and the SU2 action, as we would expect. And second, we get an extra field phi, which is determined by by a complex doublet. So this will be the Higgs field, and it acts via this matrix on our almost commutative manifold. All right. Now we want to calculate the Krein action. So as I mentioned, it's defined for an arbitrary even vector in the Krein space. And because the finite part is four-dimensional, we can write it as 4 terms. So it is determined by 4 well spinners on the manifold. So for the neutrino, we have a right-handed and left-handed well spinner, and for the electron, we also have right and left-handed well spinners. And just for convenience of notation, mostly I will group these together. So we have the left-handed well spinners grouped together, the right-handed ones, and if we add them up, then what we get is basically two Dirac spinners. So we have one Dirac spinner for the electron and one Dirac spinner for the neutrino. And these are exactly the right amount of degrees of freedom that we would expect in our theory, which is just one Dirac spinner for each type of particle that you have. All right, so if you calculate the Koen action, I won't do the full calculation, but I'll just explain the result. So here we have both Dirac spinners grouped together, and we just have the kinetic terms for these spinners. Then we get the gauge interactions. Like I said, there are no gauge interactions for the right-handed neutrino, but we get a U1 interaction for the right-handed electron, and both U1 and SU2 for the left-handed fermions. And then furthermore, we get the mass terms, including the interactions with the Higgs field. And the Higgs field acts via this matrix capital Phi, which is given like this in terms of this complex doublet Phi 1 and Phi 2. And of course, the important thing to point out is that this is precisely the Lagrangian you would find in physics textbooks. I might use different notation, so I'm not saying you could expect this notation in the physics textbooks, but if you compare it and you look at it carefully, then you can check that this is indeed the right Lagrangian you would expect for electroweak interactions. All right. So for the next two slides, I will come to the Majorana masses, which everyone has been anxiously awaiting, I think. All right. So what if we, right now we don't have any Majorana mass terms. What if we do want them? What should we do? Well, the approach is that we're going to double our finite space. So I use two identical copies of the finite space, and the second copy I will label with an extra bar, which indicates that we think of the second copy as being the antiparticles instead of the particles. And then we define some new operators on this doubled space. So for the mass matrix, I start with the one I had before. On the antiparticles, I put the same one except the complex conjugate. But now I also allow for an off-diagonal part. And this off-diagonal part contains precisely the Majorana mass. So it acts only on the right-handed neutrino, where this is just multiplied by this mass parameter mr. And on all the other fermions, it acts as 0. And of course, as you can see, because of this minus sign I put here, this new Dirac operator is no longer self-joint. It's not a self-joint matrix. But it is a Koen self-joint, because I define the fundamental symmetry now to be non-trivial. Namely, it acts as -1 on the antiparticles. Then I can extend the grading. For the antiparticles, I take the opposite grading. And lastly, I have a new operator, which is the real structure. So I didn't have this before. But now I do introduce a real structure, which just swaps the particles with the antiparticles. So it maps a particle to an antiparticle and vice versa. And it does so by complex conjugating. All right. So now we will see how the representation and the opposite representation correspond with the real structure as well. So I define a new representation on the doubled space just by the representation I had before on the particles. But on the antiparticles, I use the opposite representation of the transpose. And the opposite representation is defined in the same way. It is also the opposite representation on the particles, but the usual representation of the transpose on the antiparticles. And if you check, it is exactly given by conjugating this representation with the real structure J. So this is how the two representations are now related to each other. So basically, it's important to note I don't add any new information as far as the representation goes here. It's completely constructed from the old representation. Or the two old representation, pi and pi op. All right, and then we put all this data together. We obtain a new finite space. And in this case, it really is a Koen space, not a Hilbert space. We have a non-trivial fundamental symmetry. And additionally, we also have a real structure J. All right. So then we will look at the almost commutative manifold, constructed in exactly the same way. But now also this almost commutative manifold will be equipped with a real structure just by taking the one on the finite part and tendering it with the usual charge conjugation operator on spinners. But because we doubled the finite space, we now have too many degrees of freedom. We want to have just one Dirac spinner for each type of particle. So instead of only requiring that our generic vector eta is even, I now follow Barrett's approach and say that it also must be real. So the real structure acting on eta must be just eta itself. So this reduces the degrees of freedom again by a factor 2. One can check that j squared is equal to 1, so this is actually a sensible requirement to make. And what you find is that eta is just equal to the psi we had before in the particle part of the finite space, say, plus the real structure acting on the same vector psi. So everything is determined by the exact same vector psi we had before. And then if you calculate the Krine action in this case, we get 4 terms. So the first term is just the Krine action before doubling the space. The last term, you can check that it's the same as the first term, so we now get twice the original Krine action. But we also get additional terms from these middle two ones. But because the particles and the antiparticles are orthogonal in the Hilbert space, we have j psi being an antiparticle. So the only part that contributes to this inner product is when dA psi is also an antiparticle. And because psi itself is a particle, this means that only the off-diagonal part of dA contributes to this inner product. So it's only the Majorana mass term that contributes. So we only have to look at the right-handed neutrino inside this psi. So the calculations are not too difficult. And what you get is that these terms are just, they give you mass terms for the right-handed neutrino, which are Majorana mass terms because it is coupled to its own charge conjugate. All right, so to summarize, it is possible to also get Majorana masses in this framework. We do this by doubling the Hilbert space and then turning it into a Krine space. And what we get is the same Krine action we had before with a factor 2 plus the Majorana mass terms that you would expect. All right, so let me just summarize. So I've described the fermionic action in the Lorentzian signature, which I call the Krine action. And I hope that I've only shown you one example, but I hope that I've convinced you that it gives you the correct physical Lagrangian that you would like to get. One advantage of my approach compared to other approaches, I think, is that it is purely classical. So there are no anti-commuting variables being assumed. So the entire setup remains in the classical world. And lastly, it is possible to describe Majorana masses. And interestingly, in that case, the Krine space structure, it's not only relevant for describing the Lorentzian signature of the manifold, but in the finite part, it also appears to be relevant for distinguishing between particles and antiparticles. So in both cases, for the manifold and for the finite part, the Krine structure is relevant. So thank you.
Is there any technical difficulty in doing the full standard model, namely with color? Because you only described the electroweak.
No. It works the same way as for the Riemannian setup, yeah.
Okay. So color will not...
No.
Because there is a...
It will be fine as well, yeah.
There is a intricate way in which the left and the action on particle and antiparticle is built in the standard model. And they manage the opposite algebra to commute with the algebra because of something. So you can just reproduce that.
Yeah, it works basically in the same way here. Yeah. There's no problem there.
So when you actually insist on having even things from the very beginning, what would go wrong if you just try to do the odd case?
I'm not sure if something would necessarily go wrong, but I guess, I guess in the examples I want to construct, like electroweak theory or the full standard model, this happens to be the situation that I'm in. I guess this is the main motivation. Yeah.
So you could in
So if I want to
principle
recover
put it
those specific models, then
Okay.
that's what you do. But yeah, I mean, it
Because
should
my
be possible to
impression-
forget about the grading. Sure. Yeah.
Because my impression also from John's work is that, well, if you have something even but not real, then you have a doubling problem, so you have to project on this even thing, and that's how you define your action. If you have the additional, the real structure, then you have to project further,
Mhm.
and if you have neither of them, then you just don't project, and,
Yeah.
and that's it. So but still you can construct models, I mean.
Yeah. Okay, but I mean, if you don't do the projection, but you just start with less, then I don't think you will get out the correct Lagrangian. I don't think it fits in. Yeah.
Depends correct for what, I mean. For
Well,
instance,
compared to the physics textbook, the one that I want to get, say, yeah.
yeah, okay, but for instance, if you have M2C, which
Yeah.
is neither real nor even spectrotypal, and you still can do the same tricks and you just write the actions, you don't project because there's nothing to project to. And then you get an action for pseudoscalar particles, basically
Okay,
final
yeah,
models,
yeah.
which is a nice model.
Sure.
Can you just say more about what does it mean? I don't think I understood the point about getting using using commuting spinor variable fermion variables so you get classical spinners. I usually think of there as not being somehow classical spinners. When I do the path integral, I usually important that they.
Sure, but I'm not doing a path integral. This is, I guess, the point.
In other words, it's connected to the spin statistics business. There's nothing inconsistent about taking
No, I mean, because everything is purely classical, to me it doesn't really make sense to assume something to anti-commute if it's just a section of a vector bundle. I mean, there's no product, there's no multiplication. So what does it mean to anti-commute if there's no product? Because it's not an algebra, it's just a vector space. So it always it feels a bit unnatural to sort of ad hoc introduce Grassmann variables to make them anti-commute, whereas naturally they're just sections of a vector bundle, which are just elements of a vector space, not of an algebra. And that's it. To me, this feels more natural. Of course, if you want to do quantum theory, then that's a different story. But
also, I mean, if you would do the computation assuming that they work Grassmann, then it doesn't work. Because it will be zero.
in my case, then you will get 0, yeah.
Actually, it's 0 in your case, and
Yeah.
it works if you make them Grassmanns.
I don't think so.
Go back to the slide. They cancel.
Which slide?
The one with the final slide. No, forward.
Forward?
Going. Yeah. No, back there. The last two terms, they cancel.
Why?
What they just do. Well, you have to look at the actions that they do.
No, I don't think they do.
There's a tension between your paper stamps.
Maybe we should discuss, but I don't think they do.
Maybe let me ask another way. So normally the creation and annihilation operator you based on anti-commutation relation, and then you use classical limit to take me and you go to zero limit of theta. That's kind of a naive physicist graphical classical. When you do that, you get anti-commutation fields.
Yeah, I mean, the way I see it, the classical fields are basically like the one-particle Hilbert space, which is just a Hilbert space, not an algebra. And then you can do a Fock space construction, and you construct operators on this Fock space. And for these operators, you will want to have commutation or anti-commutation relations. That's where you start quantizing and having, because they're operators, you do have a product. But just as elements in the one-particle Hilbert space, I don't think you would introduce Grassmann variables to construct a Fock space there.
So normally to get the propagator, another way to view quantum mechanics would be to just take the path integral and I mean to take the classical limit would be to take the path integral and it's e to the IS over h bar, and then you look at it again in the h funny about having saying classical action that it's okay to have a fermion unit. Something don't know, can't recognize.
So let me make a final comment using my privilege. Something I like very much in your talk is leaving the antilinear evolution, the J for the L. I think that's the right policy. I mean, in field theory, for instance, there is the modular evolution, which is completely natural, and it changes parity and Schwarz conjugation. And I think in non-commutative geometry should imitate that. I mean, instead of trying to guess at the beginning what is the good complex structure, get this out of the physics. No more questions? We are just on time. We thank the speaker again.